This is Zhe Yu from University of Ottawa. My topic is about gaps and rings in syntenic alignments. Here we study the evolution history of the allotetraploid coffee Arabica and its two diploid progenitors, coffee cannabra and coffee eugeneides. The two subgenus that make up Arabica, we call them sub-CC and sub-CE. Then we can survey the gene loss during the 3 period. Gamma whole genome tripling in around 120 million years ago, CC-CE speciation in around 10 million years ago, and the recent allotetraploidization. Here are some of the people who contributed in Arabica Coffee Genome Consultant. This is an old slide not showing everyone. Here is the circles plot of pairs of Synteny blocks among Arabica and its two parent genomes, cannabra and eugeneides, as well as paralogous pairs between homologous chromosomes in Arabica. The chord diagrams gives a brief description on the relationship between chromosomes in subgenomes and genomes. Whole genome duplication can be considered a single event in evolutionary history that gives rise to duplicate copies of each chromosome, containing duplicate copies of every gene in the same order along the length of both chromosomes. After whole genome duplication or speciation, one of the copies could be deleted by functional or structural mechanisms, such as pseudogenization or excision, but usually not both copies will be deleted. This process is called fractionation or gene loss. When the gene is lost by fractionation, there is still a record by its paralog gene in the homologous chromosome. The similarity of gene pairs reflects the time period after each genomic event. Now we start to look at the similarity of gene pairs. Here's the histograms of average similarity of Synteny blocks with minimum size 10. We can use the peaks to locate the 3 genomic events. In the comparison of CC and CE, or sub-CC and sub-CE, the peak around 70 is for early gamma hexaploidization, and one around 99 is for speciation. Similar to the picture on the right-hand side, the comparison between parent genomes and subgenomes. The gamma event is around 70, and tetraploidization is close to 100. An open question concerning the dynamic process of fractionation is whether it occurs by single gene deletion through point mutation and pseudogenization, or by multiple neighboring genes lost through one mutation event, such as unequal crossover. So we study the frequency distribution of gap lines within Synteny blocks calculated during the comparison of chromosomes from 2 genomes or subgenomes. We start with a simple model we call one-at-a-time model. It starts with initial arrow of ones with length n. At each step, we pick a 1 at random and transform it to 0. We stop after a given number of steps, which is less than or equal to n. MTX is the notation of expected number of ring length x at time t. Here we present a proved recurrence for MTX. We believe this is a new result. The main equation explains how we gain and lost the gaps with size x. In the equation, the first term mt minus 1x represents the number of runs with length x at previous time. In the second term, mt minus 1x over n minus t plus 1 gives the probability that new deletion located at some run length x. X times the probability returns the expected value of lost gaps. Same thing for the third term. Twice the probability that new deletion located at any longer runs shows the expected value of creating new one from either two sides. The colored lines represent the number of rings of zeros after speciation and after tetraploidization. The black lines refers to the simulation of one-at-a-time model. It stopped at typical time with assumption gene length 1,600. Even when we change the gene length, the pattern is similar. It's clear that the model is inadequate to account for both the simultaneous steep drop-off from gap size 1 and the presence of significant number of long gaps. Because of the poor fit of the one-at-a-time model, we combine this model with gamma distribution composition. We compare data on runs of ones and runs of zeros from both the speciation event and tetraploidization event. We optimize the gamma parameter in terms of a chi-square criterion. Fortunately, the optimal gamma component turned out to be a simple geometric distribution with only one parameter. The distribution of gap lengths suggests that around 70% of deletion proceed by one-at-a-time model, and the rest from geometric components. Based on the diagram, we can see the combined model is much better fit on both the head and the tails to the real distribution. I'm very appreciative to the help of my colleague Chunfang and my supervisor, Professor David Sankoff. Thank you for watching.